Artificial intelligence is the combination of algorithms used for the purpose of creating intelligent machines that have the same skills as a human being. Artificial intelligence uses machine learning and deep learning techniques to extract knowledge by associating data inputs with their respective output, making them a valuable tool for industries. However, machine learning lacks human interpretable descriptions regarding how the outputs are derived, which causes humans to be skeptical. The author has proposed an architecture called Support Vector Fuzzy Parallel Embedded System by incorporating a fuzzy system embedded with machine learning. The proposed architecture goes by the acronym of SVFPS, which functions as a predictive model with an ability to form highly intuitive if-then fuzzy rules to provide linguistic insights of how outputs are derived. The author has prepared an explanation of the inner mechanism of SVFPS with the use of iris dataset. Firstly, the features of each data point are used as an input into the first layer of SVFPS. Secondly, local fuzzy clustering is performed on each of the features. Thereafter, each cluster corresponds to an antecedent node are automatically generated. Thirdly, the fuzzified values from the second layer are split into the SVM and rule layer, where SVM learns data patterns by finding a hyperplane that separates the data in the hyperspace, while the rule layer accords the explainability mechanism, forming highly intuitive if-then fuzzy rules where each node represents a fuzzy rule induced from the second and fourth layer. Fourthly, the outputs of the third layer are fuzzified values, where each cluster corresponds to a consequent node. Lastly, the outputs from the fourth layer are defuzzified, returning crisp values. After training, the fuzzy inference of each rule can be illustrated in a graphical form. Each cluster on the left represents the antecedent with its corresponding input feature. The nodes in the middle are the rules generated during training, and their respective strength of heavy and weight is shown in the bar on the bottom right. The right nodes are the consequent terms. Rule 0 can be interpreted as, if sepal length, sepal width, petal length and petal width are cluster 0, then flower is setosa. Each cluster can be labeled with linguistic terms such as short, medium, and long to enhance the interpretability. Next, the author has conducted an experiment by incorporating two forecasting technique with SVFPS as the predictive model. The first technique is called forecasted exponential moving average, where it attempts to forecast the exponential moving average. The second technique is called forecasted daily prices, where it attempts to forecast the actual prices. The results have shown that both forecasting techniques along with SVFPS manage to predict the prices remarkably, as shown by the R-square and mean squared error. The author has taken the experiment further by incorporating the two forecasting technique along with SVFPS into a portfolio management system. The motivation behind the experiment is to create an intelligent portfolio management system to assist fund managers to make early informed decisions for upside potential profit. The first experiment is conducted by incorporating SVFPS along with forecasting technique, forecasted exponential moving average, in the proposed portfolio management system. The outputs of each exchange-traded fund are used as input to the trend reversal technique, call moving average convergence divergence, for asset reallocation. The reallocation of the assets is shown by the green and red arrows, representing buy and sell, respectively. The portfolio management system with forecasted exponential moving average has shown to have an annual return on investment of 44% and outperforming 3 out of 4 of the benchmarks. Hence, it can provide an effective foresight such that investors can reallocate assets early to maximize profit gains while mitigating risk. The second experiment is conducted by incorporating SVFPS along with forecasting technique, forecasted daily prices in the proposed portfolio management system. The outputs of each exchange-traded fund are used as input to the trend reversal technique, call moving average convergence divergence, for asset reallocation. SVFPS with forecasted daily prices has shown to have only an annual return on investment of 25% and underperforming most of the benchmarks, barely outperforming vanilla MACD strategy. The author has hypothesized that the weak performance is due to the fluctuating characteristic present, which requires a smoothing pre-processing step to improve the performance. The author has conducted a follow-up experiment attempting to improve the performance of the previous experiment. The experiment consists of smoothing out the fluctuation and optimizing the hyperparameters with genetic algorithm. The experiment concluded with a drastic improvement, having a return on investment of 60%. Comparing the result with the benchmarks has shown that GA-enhanced SVFP-SFP can provide an effective foresight such that investors can reallocate assets early to maximize profit gains while mitigating risk. In conclusion, the author has introduced a novel fuzzy neural architecture, SVFPS, which has interpretability feature with remarkable predictive performance. Through multiple experiments and benchmark comparisons have shown that SVFPS can generate promising results and could be a useful tool for fund managers to obtain higher profits in portfolio management. Future works may be done for the machine learning aspect of SVFPS to improve the prediction capability of the system. Some possible improvements are replacing SVM with a deep neural network or by incorporating SVM as the classifiers in ensemble learning. In addition to improving the prediction capability, SVFPS incorporated in the proposed portfolio management system can be further developed as a full-fledged online day trading system.